My name is Kwon, and I'm a PhD student in mechanical engineering at Postech. First, I would like to express my sincere gratitude to the committee with opportunity to present at ISEV. It is truly an honor to be here. Today, I will be presenting my research on single EV sizing and phenotyping via near-world diffusion analysis using TIRF microscopy. EVs are driven from a variety of cells and have highly heterogeneous characteristics. Uncovering their heterogeneity has always been a crucial objective in the field of EV research. However, traditional ensemble analysis methods that analyze EVs by lysate are not sufficient to analyze their heterogeneity. For example, as shown in the box, it is impossible to distinguish between homogeneous and heterogeneous EV population using ensemble method. So, to distinguish between them, we need to analyze EVs at the single particle level and understand their heterogeneity. These are the three most popular single EV analysis techniques. First, nanoparticle tracking analysis called NTA is one of the most common single EV analysis technique by tracking the Brownian motion of nanoparticles to analyze size and concentration. And TIRF microscopy is a precision technique that uses penetrated light from a surface to analyze the immobilized EVs with high signal-to-noise ratio and resolution. And nanoflow cytometry is an advanced FCM technique which is capable of multiparametric EV analysis. These techniques are utilized in single EV research due to their unique characteristics. In this study, we propose a new multidimensional single EV analysis technique that combines the advantages of above techniques. This novel method is a combination of NTA and TIRF microscopy. The limitation of resolution in NTA and the possibility of bias immobilization and observation of EVs in TIRF microscopy can be overcome by combining the two techniques. To achieve this, the diffusing particles had to stay long enough for tracking on the bottom surface. This is necessary to track the particles for several frames, as the imaging area of TIRF microscopy is very thin. A simple method of adding glycerol increased the viscosity of medium and reduced the particles' mobility. In addition, accurate sizing was possible by reflecting the near or hindered diffusion phenomenon. And the developed technique can be easily applied to conventional TIRF microscopy setups. Here is the system for TIRF enhanced NTA. EVs suspended in a solution are observed in the evanescent field of TIRF microscopy and tracked for 100 frames. A constant noise frame is created by averaging the signal along the z-axis of the original movie. By subtracting the noise frame from the original movie, optical noise patterns and attached particle signals on the surface can be easily removed. Then the trajectories of particles are tracked at the single particle level for sizing. The particle coordinates in each frame are linked by the nearest neighbor algorithm, which is the most common particle linking method, and linked to the same particle trajectories. And phenotyping and subpopulation can be analyzed by comparing signals between different fluorescence channels which are observed simultaneously. In TIRF enhanced NTA, the key point is to keep the nanoparticles sufficiently tracked in the imaging area. EVs in PBS cannot be tracked for long enough times due to their small size and fast diffusivity. By adding glycerol to the sample solution, we increase the viscosity of medium and reduce the mobility of nanoparticles. And polystyrene beads of 50 to 300 nanometers were used to detect optimized viscosity for particle tracking. And it is similar size in 2D beads. Particle tracking was performed under all conditions, and the graph of mean squared displacement was used to determine if tracking is possible. As a result, beads of all sizes were trackable at glycerol viscosity of 50%, which is about 8 times more viscous than PBS. In other words, particle tracking in our system was possible with about 80% reduced mobility compared to PBS. And we also considered hindered diffusion phenomenon near the wall. If the particle is located near the wall, it will diffuse more slowly than bulk condition due to various interaction with the solid surface. The graph on right side shows the size distribution of particles calculated by normal Stokes-Einstein equation. NTA used the Stokes-Einstein equation to estimate the particle size at the single particle level, which describes the relationship between diffusivity and size of the particle through their trajectories. But in our system, sizing based on the normal equation tends to overestimate the size compared to the actual size. We applied the modified Stokes-Einstein equation to our system to reflect near-wall Hindle diffusion. When the size was calculated using modified equation, accurate sizing was possible. And we validate the sizing ability on 4 monodispersed beads according to viscosity. As mentioned earlier, tracking and sizing of the 4 beads was possible at glycerol viscosities above 50%. However, if the viscosity is too high, the particle's mobility will be too slow, and making it difficult to detect differences in trajectories and reducing sizing accuracy. It was confirmed that the most suitable viscosity of particle tracking in our system is 50% glycerol. Also, 2 different size bead mixture are distinguishable from each other population by sizing in this system. Now we proceed with EV imaging using the validated system with PSBs. This is the EV labeling process. After staining EVs by the usual labeling method, EV pellet isolated from free dyes was diluted with a glycerol solution to reduce the mobility of EVs. We optimized the labeling conditions suitable for our system. ISEV2023 CD9 cherry EVs or labeled with fluorescent conjugated IgG and CTB, which is binding with ganglioside GM1 and tracked respectively. For optimal imaging, signal-to-noise ratio, background noise, and labeling efficiency were checked according to the concentration of dye. In general, a signal-to-noise ratio of 7 or higher is good for particle tracking. And we are able to track particles over the entire range of concentrations. Considering both the background noise signal and the labeling efficiency, a suitable dye concentration is around 2 to 10 microgram per milliliter. These are the size and phenotype analysis results stained with IgG and CTB under the preceding labeling conditions. Interestingly, there was a change in size distribution of labeled EVs when compared to unlabeled CD9 M-cherry EVs in the left graph. The effect of the dye can be confirmed through the size distribution of total CD9 M-cherry population, which is red solid line in each graph. This suggests that the labeling dye can affect the particle size, and this size change was detectable in our system. In addition, to validate our new system, we compared TIRF NTA to 2 methods previously developed by our research team. One is TIRF Microscopy technique that stains and observes fixed EVs, and the other is the multifluorescent NTA, which illuminates multifluorescence light sequentially. Although each technology differed slightly in the method for visualizing EVs, each was analyzed through an optimal labeling method. In both comparisons, similar expression rates were analyzed, and we validate the analytical performance of this new system. And finally, 3 representative protein markers of EVs, CD9 and 81 and 63, were simultaneously labeled and analyzed by TIRF NTA. Markers showed high expression in order of 81 and 63 and 9, and it was possible to analyze the expression rate of 7 subgroups through localization. The graph on the right is the size distribution by phenotype analysis and sizing. Based on the expression of 3 markers, 10 groups can be analyzed, including 3 total groups and 7 subgroups. In this way, our multidimensional analysis TIRF NTA is expected to be useful in uncovering the relationship between marker expression and the size of the EVs. To summarize the research, TIRF NTA is a novel technique for precise sizing and multidimensional phenotyping of single EVs. The increase in viscosity medium keeps the EVs in the balanced field of TIRF microscopy and enable particle tracking. And the correcting EV sizing on the wall is possible through the modified Stokes-Einstein equation reflecting the near-wall diffusion phenomenon. And this versatile technique can be easily applied to conventional TIRF microscopy setups. And finally, I introduce my team. This is my lab family in the nanoparticles and vesicles lab at POSTECH. And this work is supported by the Korea Medical Device Development Fund Grant and Excellent Plus. Thank you for listening to my presentation.
Thank you very much, and congratulations to the featured abstract selection.
Thank you.
And I don't see any questions from the audience. So thank you very much. Maybe now we have one. Please go ahead.
Question. I'm curious if osmotic pressure is a concern for shrinking the size of the EV or if they uptake things that will affect the properties. Because 75% glycerol is a bit effective.
Could you tell me again? I couldn't.
Osmotic pressure will affect the
Yes.
size of EV.
Yes.
Maybe there are some controls for this.
Yes. I think glycerol affects the EVs by osmotic pressure or charge. But I always consider that. But still,
Thank you very much. Maybe we should move on. Maybe they give the opportunity to another person to ask a question.
Thank you very much. So one problem in the EV field is to count the number of EVs, and another is the heterogeneity. Have you tried with your method also to combine with some of the other cargos of the EVs and see with your technology that if you can detect the heterogeneity, for example, DNA or RNA?
Yes. We mainly stain the membrane components of EVs, but further research we will do that.
Thank you very much again.